Oh, hi there. I'm Michael Fudge, just making myself a sandwich. I hope you can't wait to take a bite out of this lesson and that you're hungry for knowledge.
Okay, let's kick off the semester with our first unit, Introduction to Databases. What's on the agenda? So we'll talk about data and metadata and the difference between data and metadata and the three categories of data. We'll look at what is a database, and we'll talk about a database management system and how a database management system is different from a database. Look at the different kinds of database management systems out there and their various storage models. We'll look at how databases are perceived, the various ways that databases are viewed, the perspectives on them, and we'll also talk about the process by which applications are built using database management systems. So, let's start by defining what is a database. A database is basically a collection of data, metadata, and data management, which is the reading and the writing of the data and the metadata. Together, those form a database. So data itself are raw and unprocessed facts, such as atomic facts, which are the lowest level of facts. These cannot be subdivided any further. For example, a postal code of 13244, that's as granular as it gets from a fact standpoint. $45, again, granular as it gets from a fact standpoint. There are also data as objects, and objects are composite. They consist of multiple atomic units. For instance, my address is 314 Heinz Hall, Syracuse, New York. 314 is my office number. New York is the state. So those are two atomic pieces inside that composite data object. Another composite data object might be a URL. You have the protocol, and then the host, and then the resource. Finally, we have data as processes or rules, and these generally take those data as objects and connect them together. For instance, you might have a customer object, and that could have name and phone number and email address and all that stuff. And then you might have an invoice object, which would have the invoice number and the date and the amount of the invoice. And you want to connect that one particular customer to that invoice. So that requires a business process or rule. So those are the three components, the three kinds of data. There's data as facts, data as objects, and data as processes or rules. Now that we've defined data, let's take a moment to define information. Information is basically contextual data, that is, data in context. Okay, it can be the output of a process. Information can also be thought of as processed data. So when you first learn to program a computer, we talk about inputs, and then the program is processed, and then you have output. So let's put data in context with that. Data are the raw, unprocessed facts, and they can be either atomic or composite. And then those are input into some process, and then that process has an output. And then whatever comes out of that process is now contextualized data. It's information. So, for example, let's suppose I have this function that I wrote called getStudentGrade, and it's written in Python or whatever, and it takes as input three pieces of atomic data. It takes the name of the student, the course that they took, and then the term, the semester in which they took it in. These would be the data as input into the process, and then the process would return back a grade, which is now information, because this A minus is not just raw data. It has meaning, it is my grade, Mike Fudge's grade in a course, IST 256, during a semester, fall 2020. So let's put this in context with an example. So on the left side, we have you, and on the right side, we have some kind of smart speaker like Alexa. So commonly what we do with these smart speakers is we ask them a question, and that in database nomenclature is known as a query. And then the smart speaker would then process the question and then give us back information, that is data in context. So here's a great example. We might say, hey, Alexa, what is the current temperature in Syracuse, New York? And that would be considered data. That gets sent to Alexa as data, and then Alexa does its own series of input, process, output to achieve information, and then the information that may come back to us from the smart speaker is something like the current temperature in Syracuse, New York is 46 degrees Fahrenheit. So exactly how the input, process, output occurs is somewhat of a black box, but it is also, in properly designed systems, not something that we need to concern ourselves with. We can just rely on the fact that it works as expected. We give it input and it gives us output. Now, we know in reality, sometimes Alexa doesn't understand the things that we're saying, and at times it can be frustrating. And so this just sort of panders to the fact that not all data begets information on the way back. So, and this is more of a function, I think, of the means at which you input the data and the type of data it is. It's really just audio that's going in there. If we were to type this information in, it would probably be more accurate, although it's getting better and better every day. Something that's really interesting is that data can be information, and information can be data. So let's go through an example of this. Let's suppose you have some data like a $200 subtotal and a 10% tax rate, and you feed that data into a process called Calculate Tax. And the tax calculator takes as input the $200 and the 10% tax rate, and you probably know what it's going to do. It's going to output $20 in tax. So that now is information within context to a process called Calculate Tax. That $20 tax can also be data in another process which takes the subtotal and the tax and then calculates the total by adding the subtotal to the tax and coming up with new information, $220. So it just goes to show you that what is data, what is information, it's all contextual within the process itself. So let's define metadata then. Metadata, simply put, is data about data, any data that describes data. And there are different types of metadata. There is label metadata. Label metadata is a visual descriptor. For example, how much money do I have? I have $5. $5 is the data. The label is how much money do I have. You commonly see labels on computer forms, right? Enter your username here, and then you type your username. The username you type is the data. Enter your username is a label descriptor. It's a piece of metadata. Also, we have definition metadata. Definition metadata provides a explanation of what the data means. So, for example, the dollar sign tells us that it's money, it's U.S. currency, the legal tender. So that's an example of definition metadata. There's also type metadata. So $5 is a number, right? So we if I take $5 and add to it $6, I have $11, right? So it follows the rules of math. It's not textual in nature. it's actually a quantifiable value. So there's different types of types. There's like numerics. There's other types of numerics like decimals and floating points, and there's also text types, and there's date types and time types. There's all these different kinds of types as we'll learn. There's also constraints, and this is something that we don't really think about when we're thinking about metadata, but business rules or acceptable values constitute metadata. For example, it doesn't make sense to open up my wallet, look in it, and see a negative number. I'm either going to see $0 or more dollars in my wallet. So that would be a business rule. You find these constraints as important because they help us keep our data valid. And this is one of the important responsibilities of metadata in a database, is to help us ensure that our data is accurate and makes sense. Some other things about metadata: we have length, which is a storage format. For example, it takes N bytes or Y bytes to store that. So, for example, if I want to store my name, Michael, I might need 8 bytes to do that. Michael, 7 bytes, 1 per each character. If I store it in a different format, I might need more. If I want to generically store anybody's name, I might need, the longest name possible for that storage format, maybe 20 bytes or something like that. So this is something usually internal. It's an internal piece of metadata, but it's very important because it helps us to anticipate the growth of the data in our database right down to the individual byte level. Location metadata tells you when and where the data can exist. A great example of that is you might not have a tax calculation in a shopping cart, but you definitely would have one in an order. So, when you're thinking about a payment process, while it's in the shopping cart, there are certain attributes that do not make any sense, but then after the order has been processed, there are other attributes that do make sense. There's also ownership metadata. Ownership metadata just explains who has access or which roles have access to the data. So my wallet has $5 in it. It's not somebody else's wallet. It's my wallet. Other ownership metadata is when, for example, you're doing e-commerce and you're, again, using the shopping cart. It's your shopping cart. Contextually, other people don't see that shopping cart. Yes, administrators might be able to get in there and look at it, but my shopping cart and your shopping cart, they're going to be different contextually. So that's basically how ownership metadata works. All right, let's talk about data management. As you recall, a database is data plus metadata plus data management. We've defined data, we've defined metadata. Let's define data management. Data management is the process of storing, retrieving, and maintaining data. Metadata helps with data management by defining a storage format, defining data integrity rules or constraints, and also defining access rules, like I can access my wallet, but you can't. I can access my shopping cart, but you can't. There are 4 data management operations. These are known as the CRUD operations because there is create, read, update, and delete. So those are the 4 things that you can do to data. You can create data, you can read it back out, you can manipulate or change data, and then you can delete data. Now, I said before, a database consists of data, metadata, and data management, but databases do not have to be computerized. Computerized databases excel in data management. The computer does the data management for us. Okay, we have specifications by which we could define the metadata, but where computer database systems really help us out is they manage the data for us. So for example, computers were built for data management. On the right is my appointments for a week in a calendaring application, like Google Calendar or Microsoft Outlook. On the left is me doing it myself on paper. And it's exactly the same data. It's exactly the same database. It's exactly the same metadata. It's exactly the same data management. The difference is one is done electronically and one is done manually on paper. Who does the data management here? Me. For example, my dentist appointment gets canceled. I have to take an eraser and erase this off. My dentist appointment gets canceled here. I just click on this and choose delete, and then it's gone. So computers are built for data management. They also help us with metadata. Like there's rules that might apply here. Like I can't, over here, I can just make an appointment that stretches across. I can draw a circle on this, and no one's going to say otherwise. I cannot do that here. I must block out times on days according to the calendar. So that's an example of data management. Computers make it really easy to do, and this is why we love computerized databases, is that they're so simple. They make it much simpler to implement our databases. So let's revisit our database definition. You're over here on the right. On the left, we have the database, and the database consists of at-rest data and metadata. There are structures and rules, and there's the data itself. And then ultimately, to get the data in or get the data out, we need data management. So there's commands you issue to the database that say, put this data in the database. And then the metadata rules govern how that happens. And then likewise, when you ask for information out, there's data management rules as part of the metadata to govern that. So, database management system. What is it? A database management system is software suited to the task of database management. So, databases can be computerized. Databases can be on paper. When they're computerized, they're easier to use and maintain. But someone still has to program all that data management. A database management system is designed to help with the metadata, help with the data management. Okay, that's the purpose of a database management system. So, common features of the DBMS. We have metadata implementation, data management, a query language that is a means to get the data, to get the information out. Data independence. This means that the way that the data actually gets stored by the database management system is independent from the commands you use to retrieve it. You do not need to know anything about the actual way that the data gets stored in a database management system. This is very powerful because if you were to program your own data management, you would have to physically figure out how to write things to the operating system in files. And the database management system handles all of this for you. It usually gives you some kind of abstraction that you can use. And in the database management systems we'll learn in this class, they use tables. So we read and write to a table, and then in turn, somehow, via some kind of magic we will learn much later on in the course, the data is written to files. It also deals with something called concurrency control. That is what happens when more than one person tries to access the same data at the same time. When they read it at the same time, when one person's writing it and the other person's reading it, or in a case when both people are trying to write the same data. There needs to be some kind of governance here, and that governance is handled for you by the DBMS. And then the only thing that you need to do as someone building your database application is understand the behavior by which the database management system will use concurrency control. Another feature of the database management system is security. This allows us to control who has access to what data in the database. We can be very granular with our security, controlling it down actually to the individual atomic data level. And then also there is a way to back up and restore data and metadata in the database relatively easily. And these are basically what make a database management system, this piece of software we call a database management system, so popular, is it handles a lot of things for you so that you don't have to figure out how to do them yourself in a programming language. So one thing you might be asking is, if I look at anything, is that a database or a database management system? Remember, a database is always some kind of application, and a database management system is a very specific application that helps us build databases, right? So database management system, it's software, helps us build databases. A database can be computerized or not. It's usually some kind of application that stores data and has metadata and has data management. We use a DBMS to build database applications. That's basically how it works. I wish I could say that all database management systems out there are the same, but they're not. It's just like all forks are not the same. There's different sizes and lengths, and they have different purposes and they serve different needs. And there's various implementation data models in the database management system, and these serve different needs. And there's no one model that really kind of is better than the other. They all have a very unique niche that they play. There are some that are more general purpose than others, but no one model is best at everything. So these govern how the data are structured and stored within the data itself. It determines the design philosophy that you're going to use. It also restricts you in terms of limitations as far as what you can do in the database. No one model is better than the other, and each have their use cases and common applications. So here's a table that lists out the common implementation models of database management systems. There is the relational model, which stores data in tables and then has metadata for defining the structure of data in columns. And there's also rules that you can put in place that determine when the data can be updated or added. So this is a very popular model. Very popular model is a relational model. It can't do everything well, but it does most things well. Another implementation model is called the key value model, and this is a very simplistic model. It's usually associated with databases that store data in memory, and it basically will store data under a unique key, and you can store anything you want under that key. So I can have a key called Mike's Photo, and I can store a photo under that key, and then I can have another key called Mike's social security number, and I can store my social security number under that key. The social security number is text. The photo could be binary. It doesn't matter. It'll store whatever you want based on the keys and values. There's also a document implementation model, and this is similar to the relational, but allows you to have some more nested and complicated structures. This is useful for representing large objects like pieces of content like blogs or composite objects such as invoices or payment histories, things like that. Those are all very useful to do in a document model. Document models also allow you to connect documents together, similar to a relational model, but they're sort of limited in their means of doing that. So you sort of have to make a decision, do I want to go relational or do I want to go document? And you'll see as we progress through the course, we'll get more into different use cases. A graph model works similar to how you would think of a graph. There are nodes, and in the nodes there are one or more labels. Like, for example, a node might be a Mike Fudge node. And then in there, I might have labels like my first name, my last name, my date of birth, my, I don't know, GPA, whatever. And then there are edges which connect nodes together. So there might be a Mike Fudge node, and then there might be an IST 659 node, and then there's an edge that connects in that says teacher. And then that forms a connection between the data object node Mike Fudge and the data object node IST 659. There might be another one, Mike Fudge, IST 659, and there's a student edge, and there's a different edge for each of the different sort of rules. What's nice about graph implementations is they're not as rigid as the relational structure. You can create a lot of different business rules that go well beyond the kinds of rules that you can implement in relational, which is why graph ends up being appealing. The downside to graph is that it's harder to query than relational. So there's also a implementation model called column-oriented. What we do is we take the data that we would normally put in a row and we store it in a column. So you might be saying, well why do this with tabular data? The table, by the way, looks exactly the same as any other table. There's columns vertically and there's rows horizontally. It's stored differently. And the reason that this works is when you have very, very large sets of data, and those large data sets contain similar types of values, like, the same person appears more than once, you can gain tremendous benefits using column-oriented, because it can not repeat the values that repeat in each of the columns, thereby highly efficiently storing the storage format. So this is sort of used for data analytics and Internet of Things type data, where it's constantly reporting device 7, and it's giving you, for example, temperature, pressure, and humidity for 9 different devices, but device 7 always reports temperature, pressure, humidity. Device 8 always does, and now you want to do like the average temperature by device. Column works well because we have now put the different devices, there's only 9 different devices in this example, into a column, so we don't have to, even though there might be millions of rows, there's only 9 different devices, so it actually shrinks the amount of data stored. Again, from your perspective, it looks like a table. However, the way it's stored is different, and it's more computationally efficient for analytics. There are some restrictions on column-oriented databases. Basically, you can't connect tables together as easily. Last in this list is time series, and time series is very similar to column-oriented, except the way that the data is written is over time. Every single piece of data that's written has a timestamp, and the timestamps are immutable, which means we cannot go back and change something that was already written over time. This makes the database perfect for time series analysis, forecasting, also Internet of Things, sensor readings, anything with super high volume writes. But what we're losing out on with time series is the ability to go back and change something that was written. So you probably heard of something called NoSQL. Basically, all these ones in the red bracket are considered NoSQL database management systems. The first one, the relational database management system, is considered an SQL database management system. It's kind of a funny nomenclature, honestly, because, the SQL language is used in some of these other types of implementation models, but what we're really talking about is the NoSQL means non-traditional style database, and the traditional style database uses this model up here. And these are different implementation models that are newer. So they all have different needs and use cases is the important thing to recognize. Primarily in this class, we will use the relational, which is really the one that started it all. And then in later units, or maybe even a later course, depending on how things go, we will talk about these other implementation models. let's talk about the elephant in the room. That is, how do you build applications that use data? Okay, or database application development. Pretty much all applications have data, whether it's a game or a banking app that you write for your mobile phone. They all have data. It's just a matter of whether or not you need a DBMS to help you manage the data, the metadata, and perform the data management activities. DBMSs make the job easier, but they can be overkill in certain situations where you just have a simple model for storing the database itself. Database management systems will make it easier to do metadata and data management, but you do have to have an understanding of design. That is, if I choose, for example, a document database, what are the proper approaches that I would make in my application development to efficiently store that document data? Even you might back up further and say, before I decide whether I should use a document database or a relational database, which one am I going to pick and why? Right? But let's suppose you already made it down to, I know I'm going to use key value. Okay, now it comes down to, how are you going to put that design to work? So in this course, we will learn design principles for creating database applications, as well as database development. We'll mainly focus on the relational model for doing this, although once you master one of these implementation models, you'll find that you have become a much better designer when you understand the storage models of maybe document or graph. You'll see that conceptually the design is the same. It's only logically that the design will be different. Okay, so let's talk about data models now. Data models are basically how we perceive or our layers of abstraction over the same database. That is, if you look at some implementation like Venmo, what are the different ways that we can look at the Venmo database? So we have at the top the highly abstract data models, and then at the bottom we have the concrete data models. That is, they match a very specific implementation. So first we have what's called the conceptual data model, and the conceptual data model is a very abstract representation of the requirements itself. There is no implementation of the database, and there is no model. So a great way to think of the conceptual data model is, let's suppose you're going to build a shed in your backyard. You might sketch out on a napkin how you want the shed to look. I want it to have a big pointy thing on top, and I want to have 2 swinging barn doors and a window on the side. Okay? You have no idea what materials you're going to need or how high or how wide it is, because all this is sort of like an artist rendering, your rendering, a conceptual rendering of it. The same thing happens with a database application. Again, if we're going to use something like Venmo, you have a conceptual model such as a user sends money to another user. Okay, that's one of the data requirements. I should be able to have a user has a balance, right? If I log into Venmo, I can see how much money I have in my Venmo account. I can also see a history of people whom I've sent money to, or who have sent me money. Those are all part of the conceptual model. They outline what's required to make it work, but they offer no guarantees as to how it's going to work. So moving down a level is the logical data model. And in the logical data model, it is taking all of the requirements of the conceptual model and building a blueprint, per se, of how the database is going to work. We offer no guarantees to an actual implementation, but we have selected at this point a storage model. So going back to my shed analogy, this would be like making a Google SketchUp or a CAD drawing, or even a blueprint of your actual shed, you would know the materials that you needed, you'd know the dimensions of the lumber, you'd know exactly the size of the shed and how many 2x4s and how many pieces of paneling and how many squares of shingles you'd need to complete the project. You'd know all of that stuff at this point, but you would have not built the shed. Okay, this is kind of the difference between a conceptual model and a logical model. Is I would never build a bridge from someone's sketch because I wouldn't know the steel and all the engineering wouldn't be there, right? In the logical model, all the engineering is there. When we are at the logical level, we have picked a database implementation model. So we have chosen either relational or graph or document or maybe a combination of those to store the data in our database. But we have made that choice, and that choice is going to affect our internal data model. The internal data model is the realized implementation of a design. So you go out and you build the shed. That's what happens in the internal data model. With a database, it would be you coding up the metadata and all the data management, if necessary, to make the database work so that you can put data in and get information out. At this point, if you're going to use a DBMS, you would have selected it. For example, I might conceptualize I'm going to make a competitor to Venmo. Then logically, I decide I'm going to use the graph model, and then internally, I would use a database management system that implements the graph model. For example, I would use Neo4j. In another example, I'm going to build a competitor to Amazon.com where you can buy products and pay for them and put them in your shopping cart, e-commerce platform galore. I might decide for that to use a relational database model. And then down here, I might select MySQL as the database that I use to implement that logical model. When you've gotten to this point, you have all of the necessary components to have a real working database. However, there are two other models that exist, so let's talk about them now. The first is the external model. The external model is the user's view of the physical artifact. So, for example, when I'm in Venmo, I press a button and I pay someone $100 and something happens, right? That code needs to be written to satisfy the user interface, right? That code interacts with the internal model. So the external model lives on top of the internal model and is an abstraction of that internal model. The internal model represents the most efficient way to store the data in the model provided. The external model is a roll-up of that to match the underlying functionality of the system. So, thinking about this with a shed, the external model of a shed is I turn the latch and open the shed door, right? The internal model is all the screws and hinges and carpentry that went into making that door work, right? Once the door works, you don't need an engineer anymore, right? Someone can just walk up and open the door because we all know how to open doors. It's pretty easy interface there. So the same thing happens with the external model is we roll up a lot of the implementation into a higher level abstraction that makes it easier to write a user interface around it. The physical data model, I wish it had an equivalent with a shed, but it doesn't. Physical data model has to do with how we actually are storing the data and the metadata that make up the database. Usually we leave the physical model up to the database management system, but all database management systems provide us with ways to tweak the physical data model. This ends up being very helpful to us because if we do not see the performance that we want out of our implementation, we can adjust or tune that performance. This really doesn't have equivalent, like I said, of a shed. in the shed example, but it's very important when you build a database application to consider the physical data model. If you use a database management system to do that, it takes care of a lot of things by default, but that doesn't mean you get to necessarily ignore the physical data model. So let's go through an example, something a little more concrete here to give you an idea of what these data models will look like. So first and foremost, we have the conceptual model. And conceptually, we have this idea of we're not going to do a whole application. We're just going to keep it simple. So conceptually, we have this idea of a customer. And a customer has these values. It has a name, email, and phone. So this conceptually means I have a thing called a customer. I want to store customers. What do I want to store about customers? Name, email, phone. These are basically the data requirements for my application. This is a very simple application. It's only going to store 3 things about a customer. Anyway, that's a conceptual model. A logical model, this is the same logical model for that conceptual model. The logical model introduces some things in italics. Okay. And it also simplifies some of the complexity. So let's talk about what's happening here. Conceptually, we have this idea of name. When we implement it, we want to probably be able to search by their first name or their last name. So we want to break those up into 2 atomic pieces of data in our database. And then we have our email and our phone. We also want to track when someone added the customer or when someone last changed the information about the customer, which I have 2 additional columns, created on and last update, that I will use to track the dates and times by which someone has added or changed the customer. Internally, I want to track these customers with a unique number, which I'm using as ID. I need some way to reference one customer over another. I do not want to guarantee that their names and emails are unique. Me and my dad are both Mike Fudge, so we would be in this customer conceptual model twice, but a logical model requires a way to pinpoint me over my father. That way, I will guarantee that myself by introducing my own key value here. So these are concerns of the logical model. This is like, again, a more detailed view of the conceptual model. You can see nothing is missing from the conceptual model to the logical model. We have simply added things that are concerns of the storage model that we've chosen, which in this case was the relational model. So now it's time to build a real thing. So we write SQL code in the relational model to actually implement a customer's table. The customer's table will implement the customer concept. And then this implements that row, and then this implements, this implements that column. This is the next column, email column, and then phone column, and then created on and last update. You can see that there's a one-to-one mapping in the logical to the internal. The only thing that's different is the code necessary to make the physical thing. And this code is going to be dependent on your selection of database management system. So let's go through an example of the external model. You might take what we had originally stored internally and bubble it back up into what we have conceptually. So I take the first name and the last name, I combine them together into name, and then email and phone. So this V customers would directly represent the concept of customer. Even though it's implemented like this, I hide things like last update or created on, which are just going to confuse the end user who wants to see their name, email, and phone number. Okay, so that's an example of the external model. The physical model deals with performance. So I might add a way to search on last name or first name through what's called an index. And I might also add what's called a unique index on emails to make sure that no 2 emails are the same. So these are rules that I get to add that physically change the way the data gets stored to make it easier to guarantee that only certain data gets entered in the first example, or to make it easier to find a user by last name or first name in the second model. Okay, let's talk about the database development lifecycle. Now that we've talked about the various storage models and the various user perception models, let's talk about the process by which we build a database application. It all starts with planning. Planning is basically understanding the scope and requirements of the problem and its boundaries. And then basically the artifact that we get out of planning is the project charter that outlines what you're going to do, when you're going to do it by, and basically at a high level how you're going to do it. It's an opportunity to identify a go, no-go, like, okay, here's what we're going to do. Does it make sense to do it? Is it going to cost us too much money to do it? Is it going to cost us too much time to do it? Basically, that's what you're going to do in planning. After planning comes analysis. And the purpose of analysis is to, now that you've decided you're going to do it, set out and capture the requirements, the data requirements and process requirements. But in a database development lifecycle, we only concern ourselves with the data requirements. So that is, what are we going to store? Why are we going to store it? How are we going to store it? Typical things that you might encounter in analysis are, what am I going to store? Customers. What am I going to store? Orders. What am I going to store? A business process of this customer placed that order. What am I going to store about customers? Their name, their phone numbers, their credit limit, blah, blah, blah. Okay. You got to capture all of that. What usually comes out of analysis is a conceptual data model. This is a high-level specification of all of the data requirements. That is, the things you're going to store, what you're going to store about the things you're going to store, and any interconnected business rules between, or process rules between those things. After analysis comes the design specification, and the purpose of design is to create that blueprint. Okay, is to create that blueprint. The outcome of design is a logical data model. There's also a plan for which you will move the data from whatever system you have now to the new system. If it's a completely new system, you will not have a migration plan. If, for example, you're using some other e-commerce platform and you're going to move it to your own, you have to find a way to move the data from one to the other. You also should start thinking about the user interface. How is data going to go in? How is information going to come out? You should build designs for those. So from a data standpoint, the most important thing is the logical data model. It's that blueprint that we talked about earlier that takes that conceptual data model and then introduces the storage model, and then with it produces an exact layout of how you're going to satisfy the rules of the conceptual model in your design. Next comes implementation. At this point, it's time to start doing and start building. So you'll build, test, and deploy your solution. The outcomes of implementation is you'll have code that you wrote which will satisfy the internal, external, and physical data models. And you'll also build the user interface in some kind of application. You can do it in Python or Java or whatever floats your boat. It could be a web application. It could be a mobile application. But it will be talking to the database through possibly the database management system that you chose at this step. Okay? And there's a lot of work to do at the implementation phase. Yeah, there's work to do at the analysis, and there's more to do at design, but there's even more to do at implementation. This final step is the maintenance phase. And in the maintenance phase, we monitor, that is, we check out our application and watch it for errors. And we also support it, that is, we handle requests and issues from users. So any users we encounter, we may need to fix. Some of those fixes are trivial. Other fixes require some work and re-implementation. Some of those issues are feature requests, which means you would actually have to go back through analysis, design, and implementation. So this process is not really a linear process. Once you hit maintenance, you could be jumping back into different phases. Let's suppose you complete it and then you decide that you want to add a whole new section. Like you have your e-commerce website and now you want to have some kind of real-time chat. built into there. You may start with planning to understand the scope and rationale behind adding real-time chat to the website that does your e-commerce, and then use that to govern whether you're going to do analysis, design, implementation, and then finally, when you release 2.0 of that website, you might now have e-commerce plus real-time chat, as an example. Okay, well, let's sum up this chapter. Database is defined as data plus metadata plus data management. Not all databases are computerized. If you're going to computerize a database, you're probably going to want to use a database management system, which is software suited to that task. There are database management systems that come in a variety of different implementation models. Some of the implementation models, like relational, are highly popular. Other implementation models are very specific to a certain need, such as column store or key value. Generally, the nature of your problem will determine the implementation model you use and you choose. Databases can be perceived at various levels, including a conceptual level, a logical level, and of course, as some kind of implementation with an internal and an external model and a physical model. These levels are useful as we're going through the database development lifecycle, because each of these perceptions has their place within that database development lifecycle. In analysis, we do the conceptual model. At the design phase, we implement a logical model, for example.